Hello, everyone. My name is Pruthvi Manjunatha. I am the iStreet Testbed Manager here at the University of Florida Transportation Institute. We will begin today's presentation with an introduction to the STRIDE program from Dr. Lilly, and then we will proceed with what we are doing with the microsimulation component, and then Dr. Hunter from Georgia Tech will speak about the emissions modeling. So with that, Dr. Lilly, would you like to speak about the STRIDE program?
Sure, and thank you, Pruthvi. Welcome, everyone. Lily Elefteriadou, I'm the director of STRIDE, which is a university transportation center in the Southeast, Region 4. Our focus is on congestion mitigation strategies, and I want to thank, first of all, Ondine Wells, who's been organizing those webinars for ongoing and completed STRIDE projects. I hope you have the opportunity to see some of our other webinars, which have been recorded, and we have approximately 1 or 2 webinars coming up each month. You see there on your screen the partners. Many of our projects are collaborative, and this particular project we're going to be talking about is a collaboration between the University of Florida and Georgia Tech. And I'm going to turn it over to Pruthvi Manjunatha, the iStreet Testbed Manager, who's been leading this project, and he's going to get us started with the team and the objectives of the project. Welcome again.
All right, thank you, Dr. Lilly. So, as Dr. Lilly mentioned, this is a collaborative project, and this is our team from University of Florida and Georgia Tech Institute. So, Dr. Hunter is lead on the Georgia Tech side, and he has multiple faculty working with him there, and we have a couple of grad students on our team at UF as well, as you can see. Coming to the introduction of this study, I'm pretty sure like most of you who are on this webinar or watching this webinar are very familiar with this image. This is like the first connected vehicle image I think we got from USDOT, and this is, I don't know how many times this image has been used in many presentations. So we are all aware of the fact that autonomous vehicle technology and the connected vehicles are here, and pretty soon we are going to see connected vehicles and conventional vehicles side by side. And when we have that, we need to have tools such as microsimulation to evaluate different strategies. So the origins of this project started to address that problem of to check whether the existing microsimulations are capable enough or not. If not, what can we do, and how can we make it better? So the purpose of the study is to come up with developing a microsimulation extension along with the emissions model, of course, to evaluate different strategies. So in this project, we are not trying to come up with a new CV or an AV logic. We are rather trying to come up with an extension that can work as a plug-and-play solution, irrespective of what kind of AV or CV logic you're using. So breaking down the objectives. So first, we evaluated capabilities of VISSIM microsimulation, and then we understood what works well, what not, and then we developed a CAV functionality in VISSIM, and then we took an example and did modeling and simulation, and then we ran the emissions with our integrated emissions modeling setup. So I'll be speaking about the first half of this project, and when it comes to emissions, Dr. Hunter will take it over. So when we looked at VISSIM and its capability to model CAVs, so we looked at it in 2 different ways. So internally, meaning like we can use the graphic user interface and just edit the existing car following or lane changing parameters and try to mimic the behavior of an AV or a CV, and externally, so using the other tools, which I'm going to explain in a second. So when we looked at the internal way of doing it by just changing the parameters, we saw that this is a very limited way of doing things. So for example, like, how are you going to do with car following? You're going to reduce the following headway because it's an AV and its reaction time is much quicker. So there's only like a limited ways of changing these internal parameters and mimic that behavior. And moreover, what we realized is there is no way to model connectivity internally using the existing tools. So if you want to use, if you want to model connectivity, you have to use these external solutions, which is basically another way of saying that it's not built into the user interface of VISSIM. So then what is the external way of doing it? Doing it externally, VISSIM offers two different tools. So one is the COM application programming interface. So this is basically a programming interface where you can, this is a very flexible and scalable interface where you can writing any programming language and access all the elements in VISSIM in real simulation time. And the second tool we have from VISSIM is what is called as an external driver model. So this is basically an external logic outside of the Wiedemann, the default Wiedemann model built into the VISSIM. This is an external driver model logic that one can write in C++ and compile it into a dynamic link library file, DLL file. And then for every simulation second time interval, this external driver model talks to back and forth between VISSIM, and then it computes how a vehicle with a separate external logic would react to how the things are changing within the VISSIM environment. So these are the two tools VISSIM gives us to model externally. So then we wanted to see, okay, like if I want to implement an AV logic or a CV or a CAV logic, how exactly am I going to go about it, and what's the best way to do it? So then we looked at both of these interfaces in terms of functionality. So what they are good at and what they are not. So when it comes to COM API, as I said, it's very scalable, very flexible. It pretty much has access to every objects in VISSIM in real time. So if I want to read a certain signal status, or I want to read a certain vehicle's location or its speed, so pretty much everything can be read from the COM API. Whereas if I wanted to tell a vehicle inside the VISSIM to do something, you can do that using COM API, but it's not as straightforward, and it comes with certain limitations. For example, if you want to do lateral control in VISSIM using COM API, right? So what you can do is you can tell a vehicle in VISSIM to change to a certain lane number. You can't really tell how exactly to make that lane change, right? If you use the COM API. So that is kind of the limitation of COM API. So it's good at reading stuff from VISSIM, but it's not really good at telling VISSIM what to do. When we look at the external driver model, it's the other way around. So it's very much capable of accurately controlling the vehicle longitudinally and laterally. So we can tell the vehicle inside VISSIM to behave exactly how we want it to behave. Whereas the access to information is not as good as COM API. So usually, if you're aware of VISSIM, there are a couple of parameters called look ahead distance and look back distance. So this is usually the distance at which the vehicle sees, right? So and whatever information you can typically get through EDM from VISSIM is the vehicles in that vicinity, in that neighborhood. So if you want to have access to all elements within VISSIM, EDM is not the right way to go about it. So what we thought of was, okay, so COM API has this strength of reading everything, and EDM has this strength of writing very well into VISSIM. So we combined the strength of the two elements, and that's how we came up with our functionality. So if you can see the figure here, so from the VISSIM we get all the traffic data. This includes the vehicle data, the signal data, and everything. So it is read by the COM API, and once COM API reads everything, it selectively sends the input data that our CV or AV logic needs. So if it only needs like 6 different parameters, those 6 different parameters are sent by COM API. And then irrespective of what kind of CV or AV logic you have, you compute that. All that COM API needs after your computation is done is for each time interval, for each vehicle, what is the next time steps acceleration, right? So that acceleration is output from your CV or AV. So from a extension or from a framework point of view, CV or AV logic is almost like a black box. Now it doesn't matter what we do inside it, as long as this is what we're sending and this is what we're getting back. This framework works. And once COM API gets that acceleration, what it does is it dumps all of that information into a text file. So what this text file has is basically an array of vehicle IDs with their estimated acceleration. So, and then EDM reads this file and it knows for each vehicle, for each time step, what acceleration it needs to implement. So EDM is purely used as a tool to implement acceleration in this framework. And it sends that information back to VISSIM, and then we see the actual vehicle movement in VISSIM. So that is our framework or the simulation extension for the microsimulation part. Dr. Hunter will explain the emissions part pretty soon. So we developed this, and we wanted to test how it works with different AV and CV logic with different levels of penetrations and so on. So we looked for the models in the literature to implement in VISSIM. So for AV model, we were able to find a paper from Talipur and Mamasani in 2016. I'm going to zoom in so that everyone can see a little bit better. So this model is basically built as a modified version of intelligent driver model. So it has a car. It has a car following state. It has a deceleration state. It has a free driving state, and the modifications are made to make a conventional vehicle behave more like an AV. And Talipur and Mamasani use certain parameters from Van Aram et al. To get the parameter values to make the AV behave slightly more aggressively than a conventional vehicle. But you can get all that details in the papers. I can share the link to the papers later. But the point was not the logic of the AV, but was for us to take an existing model and implement it in VISSIM and see how it works in conjunction in VISSIM with VISSIM. So we implemented this AV model. And when it comes to CV model, we were kind of lucky because PTV already released a snippet, a code snippet in Python to model a specific case of CV. So in this case, the application is CV. Application of CV is for the vehicle to go at a certain speed to the stop line. So basically, the logic is that if the vehicle can make it to the signal before, if the vehicle can make it to the signal before the green, it should go at its desired speed. If it cannot make it to the green at its desired speed, it drops to a slower speed, and it kind of crawls and coasts its way to the signal so that it doesn't have to come to a complete stop before the next green. So that's the basic logic of this model. Again, like if you're really interested, this is the link for the Python code snippet. You can VISSIM has already an existing built-in file. You can play with it. What we did was we took this Python code snippet and we incorporated in our bigger code in our broader code that we use to model the framework. So using these, then all we had to do to get the CAV model was to tell our vehicle to use the acceleration from the AV model unless a lower acceleration from the CV model helps the vehicle to not stop at the stop line. Right. So the CAV model was kept pretty simple in that sense, that just use the minimum of the two. So using this, we wanted to test for a simple intersection. So one of the limitations of the CV model from the VISSIM is it's made to work for a fixed time signal control. So we took a simple four-legged intersection. So we actually modeled the intersection in the University of Florida campus. This is if some of you are from here or have visited the campus. So this is right outside our engineering building in front of the football stadium. So we took a simple four-legged intersection, and then we modeled it in VISSIM. And then what we did was we took three different volumes going all the way up to a volume where it gets closer to saturation, and and then we use different penetration rate. One is everything is a conventional vehicle, then 20%, 40%, 60%, 80%, 100% of CVs, AVs, and CAVs. We have all three different models run. So based on that, we conducted the simulations, and we found some interesting results. So we just looked at average speed of the network and average delay as our performance measures from a traffic operations point of view. So as you can see, for 0% penetration, we have a certain value of speed. It's around 14 miles per hour. Just to make you guys aware, the campus speed limit is 20 miles per hour. So if something is going closer to 20 miles per hour, that means the vehicles are already pretty much going at their desired speed. So 14 miles per hour was our average speed for 0% penetration. So it went all the way up to around 15 3/4 for CAV, and about 15 for AVs and CAVs when the volumes were relatively low. As the volumes increased, the benefits also seem to increase. So from 14 to 15, all the way, if you go to the extreme side of it, at the saturation point, it goes from 11.5 miles per hour to 13. So we see not only increase in terms of compared to the conventional vehicles, we also see the increase between just the CV and AV versus CAV. So compared to just CV or just AV, we also see for each penetration level, the CAVs are showing improvement. So we kind of find similar results with the delay. So delays reduced as the speeds increase with the increasing levels of penetration, and CAVs tend to give better results compared to AV or CAV alone. While this looks good, these performance measures look good from a speed and delay perspective, we wanted to see how it works in terms of emissions. So just because one performance measure is showing something, telling a good story, that doesn't mean all performance measures are. So that's where we integrated the results from the VISSIM model into an emission model. So all our output trajectories from our VISSIM model was fed into emissions model developed by Georgia Tech under Dr. Mike Hunter. So he will take over the presentation right now, and he will explain a little bit about emissions, and we'll come back and try to summarize the whole result. Dr. Hunter?
All right. Thank you. Let me see. Thank you very much. Let me see if I can get my share screen to work. Share. All right. So hopefully you are seeing my screen now with the slides. Yes? Good. All right. So yeah, we're going to talk a little bit about putting the emissions modeling into this as well. The overview, right, what's the big picture of what we're doing, is the VISSIM model developed by UF, right? So now we have the AV and the CV in that model. Essentially that vehicle, right, they have vehicles moving through their system, and when those vehicles move through their system, VISSIM gives them a trajectory, right? So I'm getting data points every 1/10 of a second from VISSIM, and what we need to do then is take those data points, and we're going to use essentially the moves approach for this, and we're going to create the vehicle specific power, put this in the moves bins, and then generate the energy and emissions. So that's just kind of the big picture of what's going to happen. So sort of the layout. So we start with from VISSIM, it is a 1/10 of a second data, so it's 10 hertz data. We work in 1 hertz data. So we want 1 second data. So the first thing we have to do is essentially get that down to 1 second. We take a fairly simple approach. We're just taking the median speed over each second of those 10 points. We have looked at using other sorts of averaging and other approaches and not seen much of a difference in the results. And the advantage of the median is it's fast, right? So one of the things we have worked on in the implementation of this code is the ability for it to run faster than real time, because you can do this as a post process, or you can do this as, we do have this set up to run in runtime. So essentially there's a digital twin version of this that would allow you having a simulation. Maybe you're simulating the street in real time, doing the equivalent of a digital twin where we would stream that trajectory data out real time and populate a dashboard or something like that to show you what these different performance measures look like. So part of this implementation is about speed. So we generate that, so then we're going to have our individual speeds, and we're going to calculate the vehicle specific power, and then we're going to use the moves data. For the current example, we're using the 2017 fleet. We can update that to whatever the latest fleet numbers are, but that's just sort of what we had on hand when we were doing it. And then we're going to generate essentially the 1 Hertz trajectory data. So now we're going to have, for every one of those trajectory points, every second, well, here's the amount of energy or emissions or whatever you're looking for that's been generated. And then for this, we'll have different ways of sampling. Maybe we'll whatever the roadway segment, we'll sort of bundle that data into the different roadway segments so you can sort of do your analysis. For the analysis that I'm going to show right now, we did look at just through movements on eastbound and northbound, and that was just sort of so we could break it out. You can do any movements you want, but that was just for this analysis. It's kind of for brevity to see what's going on. So like I said, we get the raw data, which is a simulation. We always love a slide that's got a bunch of numbers on it, but it just sort of lets you see, right? It's just basic trajectory data coming out of VISSIM. We condense it down to 1 Hertz, as I said, and we're going to use moves to estimate the energy emissions, and then we're going to aggregate this data in something that's a more digestible form, right? Something you could put on a dashboard or something you could look at that way. Just a quick primer. I don't want to get too deep into moves, but essentially, right, we're using US EPA's moves model to predict energy consumption and emissions. So it's a vehicle-specific power calculation. We're doing this every second. You can do this, by model, by fleet, by vehicle year. You can get as specific as you wish to get. For this VISSIM application, for most of the ones we do, we just assume essentially a given fleet, right? So the 2019, or in this case, we'd say, what was the 2017 fleet? And that's what our calculations are for. But you can certainly fine tune that. The more data you got, the better you can do on fine tuning that. The way moves work, and this can get a little important in how your results work, is essentially you're going to bin the data by the vehicle-specific power and by speed. So you're going to have sort of a deceleration bin. You have an idling bin in which your vehicle speed is sort of between that -1 and 1, right? You're right in there. And then we have coasting. Then we have these cruise accelerations. So I'm binning, right? So I have my 0 to 3 VSP, 3 to 6, 6 to 9. And this is all for 0 to 25 miles per hour. And what's important about this is each bin, right, has from moves its own energy, right? So it's going to have an energy or emission. So if I'm in bin 11, I would say my rate of CO2 generation is 2598.94 grams per hour. Right? So once I take that trajectory data, I can then say, all right, every second of data, I categorize that. I put that into one of the bins. And that's going to then allow me, and then I could just sum for that trajectory. I sum up all those individual seconds of data. Here is the energy emissions of that trip. Now, for this particular work, as Pruthvi mentioned earlier, most of where we are is going to be in this first set of bins because the speed limit out there is 20 miles an hour. So we're kind of living down in that speed. But so that's sort of a concept, right? So you're doing this, you're getting the data, you're calculating the vehicle-specific power, and then you're binning that data, and then all data points within that bin are applied whatever their energy rate would be, whatever their emissions rate would be. Okay, so for our particular study, like I said, what we did is we looked at, for the results right now, we're going to look at the CO2. Again, you can do anything because you got that, use your table apply as you want. We looked at the eastbound and we looked at the northbound, and we broke down into 2 parts. I looked at the entire route through, but we also collected data on just the up to the stop bar. So essentially you could sort of capture that queuing part and the deceleration, and then you do the full route, which would also then give you the acceleration out of the intersection. The results I'm going to show for eastbound, the northbound essentially are about the same, but again, for time and brevity, let's just talk about the northbound. As mentioned earlier, we're pulling the data from the trajectory runs, from the VISSIM runs that were done by UF. So we're looking at, V overseas of 0.7, 0.85, 0.9. Well, trying to capture sort of a range of not very congested to more congested. Penetration rates for CV, AV, and CAV of 0 to 100 by 20s. We did 5 replicates for each scenario for what we have our runs. So all the data you see is actually based on 5 replications. The runs were an hour. We tossed the first 600 seconds for warm up. So the analysis is actually based on the 600 seconds to 3,600 seconds. We can get a big long debate with the simulation folks about what's the right warm-up time and all that kind of stuff. But this is a pretty short pretty tight little intersection. So 600 seconds, 10 minutes should be fine. So let's look at travel time for a second. Now, we already saw some travel time. What's the difference here? What you're going to get to see is, of course, this is over the 5 replicate trials, and the numbers are a little different than what you saw earlier because we're only looking at the through movements, right? So this is just eastbound through, and it's, but now you can see what the mean value was, what the median value was, but we can also start looking at what the range of values that we saw. And as was mentioned earlier, it's kind of nice, right? For the travel time, this is 0.7. You see as the AV percentage increases, and I have the CV percentage increasing and the CAV, a general trend down, right? So we're seeing some improvement as I put each of those options in. And, you know, you're also seeing some minor decrease in the amount of variability, right? That range between the 25th and 75th percentiles is tightening up a little bit as well. The left side is from the start to the stop bar, and then the right side is the entire thing. We can also then turn around and look at, so the V over C of 0.9, so now we're getting a little more congested, and you can see the impact of these methods matter more, right? So you can see that the AV is giving you a better improvement under those higher V over C conditions. Same thing with the CAV, same thing with the CV. Again, we sort of see similar results between the two graphs. Great sins committed in this graph. I'll readily acknowledge that, and we will fix it in the final report, and that these are not on the same scale, right? That's up to 80, that's up to 100. Such a thing should never happen. We'll get that fixed. So we're doing this decrease, and you can kind of see, all right, so you've kind of seen that, that's great, right? We see the travel time. So what happens with the emissions? So the emissions, all of a sudden you see something that, well, let's look at the 0.7 V over C. Again, looking at the logics we had. For the AV, it's doesn't really do much, right? So the AV is not impacting the emissions all that greatly. The CAV, for the implementation we had in the model we had, the way we did it, actually gets worse, right? So the travel time was improving, but the emissions, right, the CO2 at least, is increasing, right? So as that penetration rate goes up, you're going to increase. The same thing with over the entire route and just that up to the stop bar version. And if we look at this under the 0.9, the higher V over C, we see this is even a bit more, a bit more dramatic. Actually, in the higher V, the AV gives a little bit of improvement, but the CV and the CAV, you're going to start seeing these increases. CAV, there's sort of a balance between the AV and the CAV part, or the AV and the CV part. So the mean doesn't change much. You gain a little bit on the median. However, the variability is increasing, right? So that range of values you're seeing is increasing. And that ends up becoming an interesting result, right? So we want to explore that a little bit and sort of try to get a sense of what's going on, say, with this CV. Why are the emissions getting worse? And kind of dig in just a little bit. So what we did is we can look at this for the 0.7, V over C of 0.7. I can look at an increasing rate of connected vehicles, 0, 20, 60, 100. This is the amount of data points, right, in each bin. So every second of data, right, becomes a point in that bin. And you'll see, right, for idle, right, the first operating bin, when this thing first starts at 0 penetration, right, about 33% of the data actually fell into that idle bin. And when I go to 20%, right, hey, it's decreasing. 60% decreases by 100% penetration of the CV. That algorithm did exactly what it was supposed to do. I have almost nobody idle. They're not sitting stopped. Now, the question, of course, becomes, what are they doing when they're not sitting stopped? How do they get there, and what's the algorithm actually causing that vehicle to do? Well, that's where this starts to get a little tricky, is we'll notice you see an increase in what moves essentially we're going to have bin 12, right? And that's cruise acceleration. It's still a low VSP. It's from 0 to 3, and that's the 0 to 25 miles per hour. But that's bin 12. And you're going to watch that as the penetration increases, the amount of time the vehicles are spending essentially in this cruise minor acceleration. So what we actually observed out there was an oscillation, right? So essentially you're seeing an oscillation as the vehicles are going up to the quarter. So they're not going to be stopped at the signal, but to do that, right, what's their behavior? Well, where does that get me in trouble? Well, in idle versus in that cruise acceleration bin 12, well, that's got almost twice the emissions. So we gain a little bit maybe in time, right? So there's not going to be as much time because the travel time, decreased a little bit, but we're paying the price in emissions for just how this is working. So there's a trade-off, right? Now this is, not giant, we're not giving some kind of earth-shattering result here, but it's interesting to see it, right? This is why, you see the papers out there right now on multi-objective optimization for CV or AV, that you can't just work around one parameter. You need to be looking at multiple parameters. This is at the 0.9, and the 0.9 is even quite a bit more extreme, right? We start with 1. That would be people just sitting there waiting, and it drops as that penetration goes up. The algorithm's doing exactly what you want it to do. However, the way it's doing, right, is not considering what the impact is, right, on potential other parameters. So we're seeing this bin 12 data, right, increase, and again, that's forcing this increase on the emissions. Now, let's be sort of careful about what we're saying here, and I want to talk about that a little bit. So first of all, in our method, yeah, we said you can do this, right? You can apply this. That we've kind of taken this through the full process, put the CV in, put the AV in, carry this forward. Can do something like moves, can do it in real time and runtime, right? This is a feasible thing to do. And we also have these findings that I just mentioned, right? That you can have AV did seem to improve, but in the CV, hey, you did better in one thing, but you did worse. And this is actually quite important, right? Now you have a platform, and that's what you want to do. You want to develop a platform, a repeatable method that people could test their different logics to find those kind of things. However, right? Let's think about it a little bit. Sorry, I jumped ahead of myself. It's possible, right? So a control algorithm might improve one performance measure, such as trial time, but not another. Again, multi-objective optimization. We got to look at all these things. So having that ability to explore that. However, let's be kind of careful about what I just said. I'm not so much worried about the results as the potential. And that is, so we need to confirm some things, right? Let's go back and make sure that we got that implementation correct. I certainly believe we have the implementation correct, but we're looking at it to make sure. But then you have to ask, all right, so is the AV and the CV modeling realistic? So are those models the way it would really work in the field, or have they been designed really to sort of capture one aspect, right? So we don't want people to have to stop at the light, but that really isn't the behavior you'd want to implement for people to stop at the light. That may be causing a trouble. Another side of that may be, how are the non-AVs responding? And are the non-AVs responding in a realistic way? So we need to explore that modeling. We also have to look at just how we've done the emissions model itself. So, there's a trap in here that we need to explore, and that is, I put those bins in there just to remind us this is a binned approach, right? And you can always get in trouble when you have that sort of approach. There's some sort of, underlying assumption that the data is kind of randomly spread out through each bin, and, it's okay to sort of take every vehicle, that fell in that bin and apply the same number. But it is certainly possible that when somebody implements one of these logics, that suddenly some of these assumptions we've been making may not be true, and then it might be that what is happening is a lot of the data is actually right at that 0 VSP or right near the 0 VSP, and to apply it to the factor that would be from 0 to 3, we might actually be overstating what's really happening. So we have to look. We have to make sure the method of the calculation itself is not creating a bias in the final result. So those are some of the things that now become important that maybe we didn't care as much about before. Terrible way to say that. But maybe we didn't worry as much before we were trying to see what these technologies did. But now these technologies are reacting differently than people react. And that might cause us to create and see some biases that really wasn't affecting what we were doing before. So that's one of the things about this particular effort that I found interesting myself, is that it's really sort of creating this, these models really weren't built to do what we're doing with them. And now we've got to make sure that we're not uncovering potential underlying biases in what these models are doing simply because of the technologies we're using. So that is what I have. Pruthvi, do you want to jump back in and do the last slide or two?
Sure, I can share my screen again. Yeah, so just to recap everything, so we did evaluate the capability of VISSIM to model CAVs, and we found that internal modeling is not the way to go. Externally, we realized that we have to use a combination of both COM API and EDM, and then we went out and we developed that framework. Then we did a simple implementation using an AV model and a CV model. We realized that we do get good results in terms of traffic operational performance measures, but as Dr. Hunter just wrapped up, emissions models is a different thing, and a couple of things we need to do is, to investigate further, where are these oscillations are coming from, what additional feedback our framework needs to make a more realistic implementation. And as he said, for the future, when we think about optimization, so we some of the things we are working on, how to optimize signals based on connectivity and so on. So it's important to not only look at just one objective or one set of performance measures. It's it's important to do a multi-objective approach where things like emissions are considered as well. So that is the natural future work for this line of work. Before we move on to the questions, I've been told by the Stride Center to make sure that everybody answers this survey. So I'm going to copy this and paste it in the chat box so that you can go ahead and complete the survey for us. And meanwhile, you can also take this opportunity to enter your questions on the chat box. We'll give everyone a couple of minutes to complete the survey and as well as ask all the questions.
While they're filling that out, why don't I was looking at the chat. I can start answering one of the questions if you want.
Sure.
I know one of the questions was, and it's a great question, how well do the bin distributions from the VISSIM trajectories fit the bin distribution of real vehicles, right? So we've always kind of know, I'm going to paraphrase here, but that something like VISSIM or a lot of these models, the traffic's just smoother than it really is. Absolutely, right? So that's really what the big question is we're going to look at. So at heart, I'm an operations guy. That's a lot of the kind of work I did. What's the delay at the signal? What's your level of service? All that kind of great, wonderful stuff. And at that point, I didn't care, right? I mean, if the travel time was right, then the travel time was right. If the delay was good, the delay was good. But now when we start trying to do some of these other things, we try to apply these models to something like emissions, suddenly, these internal variability that maybe the models aren't catching well, that didn't really matter when I was aggregating something like delay or travel time, suddenly you're going to start mattering when I'm looking at the data from this point of view where I'm trying to pull it out every second. So absolutely, and that's exactly one of the kinds of things we were looking at to see, is this an issue, right? Is the realism in VISSIM appropriate or in any simulation tool for a second-by-second analysis like that? So that's absolutely great point, and it is something we're looking at.
Okay, I am looking at another question. Is estimated acceleration from COM API to text file to EDM to VISSIM different from acceleration from CAV logic to COM API? No, it is not. It's basically the same acceleration. The reason we use EDM to implement the acceleration is one, COM API cannot implement the acceleration directly. It can, however, implement something like a desired speed, which comes with its own caveats. And moreover, like if you want to do something like a gap acceptance or a lane changing, it can't be directly done through COM API. So as a framework, we wanted to use EDM so that it's a plug-and-play solution irrespective of what applications you're using. So if somebody wants to use this framework and implement a lane-changing model, they can, because we have routed it through EDM. The second question I see here is, did you account for pedestrian movements at the intersection and at pedestrian crossing? No, we did not use any pedestrians. We wanted to keep it simple applications. Our emphasis was more on the framework than the application or the use case. So we did not consider pedestrians.
Pruthvi, this is Lily. If I can jump in for a minute on this pedestrian related question, just to let you know that we have a parallel project that's funded by FDOT where we're looking at the impact of pedestrians on signalization and the optimization of signal control. So hopefully as a continuation to this project, we will be able to account for pedestrians. Thanks.
Okay. Okay, so there is another question. Can I separate connected vehicles from autonomous vehicles? That is to say, one can analyze the impacts of autonomous vehicles without talking about the connectivity of vehicles. Yes, you can. And if I go back to our slides, that's what we did. We looked at AVs separately, impact of CVs separately, and then we looked at the CAVs. So if you look at this graph, our blue line is what you're speaking about. It's just the AVs without having any connectivity modeling. Okay. Can the VISSIM model simulate the CAVs receiving signal timing information from the controller and respond accordingly? So yeah, that's what we did. So the CV code snippet that we use from PTV, that's what it does. So it tells the vehicles how many seconds of green is remaining or red is remaining. Yeah, the short answer is yes. Okay. Dr. Hunter, do you have any questions that you want to pick up?
Am I muted still? No. Okay, so we have, can we apply this methodology to a larger road network? Certainly can, and actually we're starting that on another effort. We believe we've worked out the details of how to do this. It's just a matter now of really scalability, and then you got to look at scalability. And one of the issues that I know Pruthvi didn't really get into much is we're going to get into how long does it take to do a run, right? So as I start scaling, the model's going to run slower and slower. So those are actually going to be some of the real issues that are going to start coming into play is the scalability. I'll leave you for the R question. How confident are you in your simulation results? So depends what you mean. I'm fairly confident that simulation results that we've done everything correctly. That's fine. Whether or not the logic is a fair reflection of how things would look in the real world, I'm actually quite uncertain of that, and I'll be quite honest with that. And in some ways, it's very difficult. How do I calibrate something that doesn't exist, right? I mean, other than a few test track examples, there really isn't a great set of examples for how this really works, and there certainly isn't a great set of examples for how people are going to respond right to the AV or respond to the CV or use the CV. So you actually have some challenges here that we are making a lot of assumptions, and I think every study that exists is making a lot of assumptions. That's just sort of the nature of the beast right now, because field data doesn't exist. And when the field data exists, then we can do a better job on the calibration.
Yeah. Okay. I think we just got one question. It was stated that VISSIM's internal ability is limited. Can one still use internal ability for just autonomous vehicles by changing the parameters? If yes or no, how far will the result be from someone who did not use the external ability? I mean, yes, but it will be extremely limited because you have only certain parameters to play with within the Wiedemann model, which is used for the internal modeling in VISSIM. So, so if you want to compare it with a different AV logic, it depends on what the other AV logic is. So, yeah, it'll be like, we all know that calibration to mimic certain behavior, you can only get so much. Dr. Hunter, do you want to add something on that?
No, I think that was good. I was looking at there's another question on with emissions saying for CNG vehicles, fuel and emissions, would this change? Absolutely, right? So if you're using CNG or an electric vehicle or whatever, again, what you need is the underlying model, right? So, here we're using moves VSP to do those calculations. We're generating the trajectories, and then given that trajectory and those performance, what is it for electric? What is it for CNG? You need the model, but if you have the underlying model, you can certainly make it work.
Okay, so yeah, there's a question. I think we kind of addressed it, but somebody was saying, did you use single core? Did you face an issue simulating? Yes. So I'm not the expert in the number of cores and how it has impact on the actual simulation time, but yeah, we did find the simulation to get slower and slower as we increased the percentage of AV or CV in our code. So when we want to scale it up to a bigger network, that is a problem we have to. That's a challenge we have to resolve. Yeah.
Yeah. The only thing is, I'll add to that is we're starting the process of trying to look at exactly how VISSIM works with cores and try to do some bench testing in that, but I don't quite have those answers for you yet. Well, I'll say, historically, what I have done with trying to run something like VISSIM is I try to throw as much RAM at it as I can afford. Right? It seems to do a pretty good job using that memory.
Yeah.
Pruthvi, there's a question there about, can RStudio be used for calibrating CVs or only Python?
So I think the question is more on like what programming languages COM API is compatible with. So I'm not sure if RStudio is on that list, but certainly most of the programming languages like C++ or Python or MATLAB, I'm pretty sure they're on the PTV list. So if somebody from PTV is listening in, you can answer that question.
Somebody asked the presentation file. That will be made available, right? All participants will receive a copy of the presentation file.
Yes, and also I believe recording will be uploaded onto the Stride website.
Somebody said the link wasn't working. Is that an up? Did you update a new version of that link to make sure it's working now for the survey?
Yeah, I think I think Ondine posted the link again.
Okay.
Yeah. All right. So I think that those were the questions. Before we end the webinar, we would like to speak a little bit about the upcoming webinars. So myself and Dr. Lily, we are going to be doing another webinar next week, same time, on the iStreet initiative. So around a year and a half ago, we did a presentation on iStreet. We introduced the program to everyone through the Stride webinar series. So this presentation will be both for the new audiences as well as the old ones. So we will reintroduce the iStreet program, and we are going to give updates about the key projects and what's going on with our program. So as Dr. Lily mentioned, on one of our projects, we are indeed considering pedestrians in our optimization problem. So we are going to talk about projects like that next week this time, and next month we also have another webinar coming up from North Carolina State University. Please sign up for these webinars using the link provided below. So if you have signed up for this webinar, it's pretty much the same link. All right. So I think we have one last question. How do CAVs play a role in oversaturated conditions? Yeah, that's something we need to investigate, why we are getting better results with increasing levels of saturation. That's a good question. Yeah. Dr. Hunter, do you want to add anything?
No, I mean, the honest answer to your question is we only went up to 0.9 V over C, so we didn't look at oversaturated. That is something that, we can look at, implement these same models, future runs with V over C's exceeding 1 and sort of see what happens. The last question I'm saying is can VISSIM be used to simulate the impact on infrastructure, the impact of infrastructure on CAVs? That's kind of vague. I would say it depends, right? So what is it you're trying to model? I mean, certainly you can capture grade, you can capture these kind of things, and you'll see what that behavior is. So I guess I would need a little more detail on the question. I would say VISSIM capturing the impact of infrastructure on vehicles, right? It doesn't really matter if it's a CAV or not. It can capture the impact of certain infrastructure changes. So yeah, you can. But again, you gotta be more specific about what it is you're hoping for there.
Yeah, this is Lily. I would say that we're limited by the existing models of the relationship between the trajectory of any vehicle, including a connected autonomous vehicle, and how it reacts to given portions of the infrastructure. And if we're talking about signal control, there's a certain reaction. If we're talking about grade or width and cross section, and it's a different reaction. But we kind of depend on the existing models for that, and we have to make assumptions on the models that were used to replicate autonomous connected vehicles.
Right. So with that, if you have any questions or comments, please email us. We can talk about it later as well, and please do sign up for our future webinars. Thank you so much for attending this webinar. The questions were really insightful, and we had a good time presenting this.
All right. Well, thank you to everyone.
Thank you.
Bye-bye.
Bye.